Okay, I just booted up RStudio and we're ready for another session. Today's session will focus on Chapter 5, all about dplyr package, which is part of the tidyverse package, and it has lots of nice features in it to help us manipulate the data. So I have a piece on here that just some pieces I'm going to get rid of. And so maybe when you come in here, this is what your window situation looks like. We're going to go in. In a previous project, I asked you to download the Chapter 5 code. All right, so to download the file then, if you put it into your downloads folder, just go there and select Chapter 5 code. Version 2, it looks like. And there you can see the YAML heading and the rest. Now, I've designed this so that it's an R Markdown file. Basically, I like to hang an R Markdown because when I click on these little right arrows here, it'll run the code. So here we are. What I'm going to do here as well is to minimize these windows. Of course, just for a refresher, this is the environments window. This is the output window where you can output plots, and you can see all the packages or install packages, see the help for particular commands. Here is your console. This is where you want to your output for your code up here in the content window, the source window. When you run this content, it'll run in here, but it'll also run down here. And because it's running in two places, I'm going to minimize this console window. There may be times when I would like to bring it back up to see what's in it. So it's pretty much minimized now. Now, when I click this double window, that's where you get both windows, and then you can come up here and drag and kind of shrink it a little bit. So I'm going to enlarge this window here so I can just see the environments. And I don't use this one down here. A lot of times for the plots window, you're going to see plots down here, but because of the R Markdown file, you're going to see the plots right in the R Markdown window. So I'm going to minimize this one as well. The other thing I'm going to do is zoom in so that when you're viewing this online, you can see it a little better. I'm going to put my cursor to the end and do Control Return to run the tidyverse package. You always want to run that unless you hear otherwise. The dplyr package is in there where we're going to use a lot of our commands for today. We're going to be introduced, and the first thing I'm going to do is go through this data on the New York City flights from 2013. There are 3 local airports in New York City, 2 out of New York City and 1 out of Newark. So we look at all of the flights taking off from those 3 destinations in the year 2013. But it turns out that there's like an unbelievable number of flights that take off from those destinations each year. All right, now inside those packages, we're going to install some libraries we're going to use. And so I'm just going to install all of these at the same time. So if you want to make sure you're dealing with flights, you can give the package name followed by 2 colons and then the flight. And when you do this, you're going to see an abbreviated tibble of the New York City flights. And so if you click over here, you can see the other fields. You'll see here that there are 19 different columns or fields: year, month, day, the departure time, scheduled departure time, and then if you subtract those 2, you get the departure delay. Then you have the arrival time, the scheduled arrival time, and then the difference of those 2. The carrier is the airline. United Airlines would be these. There's Delta and some others. And this is the flight number, and this is the ID number of the plane. This is on the tail of the plane. And this is the origin. And remember, this is the Newark Airport, and LaGuardia and JFK are the other 2 airports in New York. And all of these here, there's many more over here because the destinations where the planes from New York go are numerous. All right, so in addition to the destination, you got the time in the air, the distance in the air. So this is kind of like a time date stamp over here. Now, the air time you can see here is 227. I believe 227 minutes. Now, when you put a question mark in front of the New York City flights to look at those flights, it gives you the information. This is one time that I'm going to enlarge this pane down here so we can see all the information about the flights. So year, month, and day, departure time, arrival time. You can subtract those 2 to get basically the length of the flight, scheduled time, departure time, and arrival time, and then the delay. The delay when you take off, the delay when you arrive. And then you've got the carrier, flight number, the tail number, the origin airport, destination airport, The airtime is the amount of time spent in minutes. So if you divided the airtime by 60, you would get the airtime in hours. Give you the distance between the airports, and then they give you the hour and the minute to schedule the time of departure. So 5:15 a.m. and here's time hour. Now, if you don't have a couple of these columns, we'll create them. I always say that it's good to research your variables and know what each of them mean, because you're going to be performing operations on them. And if you're performing operations on them, then you need to know, what the data is all about. So I'm going to minimize this window again. So over here, you can see the type of variables. You've got integer values, number values. Okay, now when you say view the flights, it gives you this entire grid, the entire data frame. And so I'm not going to scroll through it, but what's nice is that when you do the view command, and I would say only do it once, because when you do it once, it puts the flight's data frame up here along with your code. So if you ever want to go back to your code, you just click this window here and go back. All right, and then here are the standard abbreviations. I got this funny notation around it because when you render this, then it'll put it into a nice list. But basically we have int, dbl, which stands for doubles, which are real numbers. And then you've got these character strings, which are qualitative variable, and then the date timestamps. And there are some other ones as well that we won't use a whole lot. Remember, when you run flights from here, it will give you just about 10 rows. So I would say view the data flight at least once. That'll put the flights data frame up here. So, when you're doing your code down here, you can always click up and take a peek at the flights again. Per head is something that's useful because that reports the first 6 rows. And so if you want to see the flights information, you can go up into the global environment, select the flights, and then the flights data set will come up here. If not, you can type it over here, flights, and then it'll come up. All right, and then clicking down here, you'll see all the variables. Right now, you can see 336,776 different flights from those 3 airports in 1 year. So notice that the year is always 2013. All right, so now it's always a good idea to investigate the data a little bit further. If you find that you don't need to see this, then you can skip ahead to the code from this section. Just skip ahead in the video. But what I'm going to do now is just take a look at all of the different variables and what we're talking when we look at the data. So this is your standard. Graph. You start off with the ggplot command and select the data. Basically, that's all you need to have in the first layer. I am assigning this first layer to K so that I don't have to type in all of this. Again, if I just want to refer to this line of code, I'm just going to call it K. And then this one here will create a table of all the carriers, and then we'll draw a bar graph of all the carriers. You'll see 2 places where you'll see the table. And you'll notice here that you have the table, but the table is also down here in the console window. A lot of carriers, and so here would be a better representation, the graph. And you can see that United Airlines has the most flights out of New York City airports, followed by B6, Delta, and EV. So you got a sense. We have some airlines here that have very few flights out of New York. For this one, I'm not going to draw the graph because there's just too many different tail numbers. Each plane has a different tail number. And so what I might do here is just to run the table just to show you that it's the graph is not going to be a very interesting. You can just see all these different tail numbers down here. For example, the way you would interpret this is that this particular plane took off 163 times from New York. It gives you the nice information, but if you took a look at a bar graph here, you just have so many bars that it wouldn't be very worthwhile graph. So for flights, the origin, I said the origin was the local airports, JFK. So you can see the table here. This is the Newark Airport, and then these 2, JFK and LaGuardia. So about over 100,000 from each. And you can see the bar graph here. All right, in this next graph, again, it doesn't have our markdown on it, but this would be the destinations. And so I'm just going to go ahead and run this one set of codes so you can see these are all the airports down here where New York flies to. Let's see if we can find Detroit. There it is, DTW. So there are 9,384 flights during the year to Detroit. Time, hour. Again, time hour is this variable down here that is like the date stamp. And so it looks, there's probably going to be 365 of those. So I'm not going to take a look at that. And it says the date uses 3 different fields, day, month, and year. And so it makes sense then if you take a look at those three. It's not very interesting because when you look at a histogram of the flights, you can see that during the month there are like 31 different days, and there's about the same number of flights each day. When you look at the data for months, well, how many months are there? Well, there they are, 12 months, and you can see there's about the same number of flights taking off from New York each month. And when you look at the year, this one is not very interesting at all. There's just one bar because every single flight occurred in 2013. All right, now as soon as we get to some of these numerical variables, then it makes sense to look at a histogram. So generally my rule is that when you're looking at just a single set of data, then plot it with a histogram. If you're looking at multiple and you're comparing multiple data sets of numerical data, then it makes sense to use a box plot. But here's the histogram. You can see this is a skewed right graph. Most of there's a couple of flights out here in the very long minutes, but most of the flights will last between 0 and 400 minutes. And if we say 300 minutes, that's 5 hours. So most of the flights are less than 5 hours. If you want to represent that in a different way and looking at a box plot, this is what it would look like. But again, I think box plots are more useful if you are going to be comparing two different numerical data sets. We can compare the distances again. So just like the times are skewed right, so are the distances. And if you want to look at a box plot, you can see that there are a couple of data points up here that are outliers. So that one's a little heavier dot than this one. So probably the case that they fly to this destination 5,000 miles away a lot. All right, so here's my K. It just gives me the ggplot command and selects our flights data. So now we're going to do a scatter plot on the horizontal axis airtime, vertical axis distance, and then the origin. Those are their three airports there. And so we're going to have three different colors. So one color for the Newark airport, one color for the JFK, and the other one for LaGuardia. All right, they're plotting a lot of points, so it takes some time. And they said they removed 9,430 rows of data for some reason. But here you can see a combination of reds and greens and blues. And, you can think of this data and you can say, okay, well, here are the domestic flights, and then maybe they stop at one flight in the ocean, and then this might be Europe. So you got this huge gap where they're not flying this distance. It's because there's a big ocean there with no lands. In this one here, we're going to do another scatter plot, but this time we're going to compare air time and distance, the same two variables, but now we're going to select the origin to be the shape. Remember, we have 7 different shapes. Since there are only 3 different origins, we're going to have just 3 different shapes. So notice the color is not there now, but there's so many different flights that this just gets clouded in here. But you can see the rectangle and the circle and the triangle there. They do give the 3 different shapes. When all those points are kind of clouded together, sometimes a transparency command, it's the alpha command, will make the points look a little lighter, and that way heavy chunks of points will be indicated with darker blue spots. So see the transparency here, and it's a little bit light. So you can see there are fewer outliers here than in here where it's dark. And then you have dark, 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 and it starts getting lighter. If you just removed the alpha factor there and ran again, you would see there's no transparencies in these lighter outlier areas here. Yeah, and so here's an example of if you're looking at comparing numerical data of 3 different groups, then it makes sense to have a box plot. You can see LaGuardia basically stays in the United States. No flights over here. Newark and JFK, it looks like they fly to Europe. Various other places, I'm sure. Now, this one I couldn't use K because I'm going to start to filter. This filter command is going to be one of the key commands that we use. So here's an introduction to it. And what we're going to do is basically plot the same data, but we're only interested in those flights that have a departure delay that is negative. And so if the delay is positive, like 10, then that means that the plane was delayed 10 minutes. But if the departure delay is negative, that means that the flight actually left early. We're going to color by where the plane took off by the origin. This is a box plot, so we really don't need any markers on the y. So I'm just going to say y equals, there's nothing between these two quotes. And so that basically means it's going to print nothing over there on the vertical axis. And then we're plotting departure delays so we can see them. Now, because we said we wanted departure delays to be negative, here's 0 and here are all the negatives. So there are a lot of flights here that leave early. This one here, this point here left about 33 minutes early. You can see they all leave early on various occasions. Here's one that left, this green one here, left more than 40 minutes early. Interesting, probably an international flight. Okay, getting into now the chapter 5 package called dplyr. This one here, if we come up to the tidyverse, there it is, dplyr package, and you can type in some of the commands there. And then when you type in one of the commands, then it'll tell you the syntax, how you need to use that. And the other ones that we're going to use are arrange. This is our sorting command. Arrange, there it is, tells you. And there are other ones that we're going to use in this section, and I kind of summarize them up here. Usually when you have a data set, in our case here, the flights data set has 19 variables. Well, when we want to look at a relationship between variables, we don't want to look at the relationship between all the variables at the same time. It's usually we want to look at the relationship just between maybe a couple of variables. What we want to do then is to filter out the data and create a plot based on the filtered data, or create a table based on the filtered data. You use this command a lot. In fact, you're going to be using a lot of these functions here to manipulate the data. They basically call these functions verbs. So you can call them verbs or functions because they're action items. And the first argument that you always use in these commands is the name of the data set. So over here, you can see that you're going to use the data. And then after that, a bunch of commands that we will, and there's a bunch of similar commands that we use. All right, arrange is the command that we use to sort the data. Select is how we select variables, maybe for display. Mutate is where we create new variables from old, and we don't add it to the data set, we just create the variable so it's there. So even though it's not in our data frame, we can use that variable that we create using the mutate. And then for summarize, of all the variables that you have and that you've created, you can basically tell which variables that you want to display, and that's using the summarize command. And then the group by command, if you want to break down, say, origin into the 3 different airports, then you would say group by origin. And if you're drawing a graph or something like that, then it would draw the 3 different subgroups instead of the whole data set. All right, I'm going to put this piece 151 to 155 here frequently every time we see one of these commands, just to get you in the habit of thinking about, okay, the first thing I have to tell these commands is I have to give it the data set. And then after that, you give these subsequent arguments that basically describe how you want to filter. Sometimes you use variable names with quotes, other times you don't. In this case, you use them without quotes. And the thing that you create after you run one of these functions is a new data frame. You're basically going out and grabbing a subset of the data to work on. And what's important is that if you think you're going to use that data frame in the future, you're going to want to assign it a new data frame name. Okay, so we're going to go through these in order. Filter allows us to choose a subset of the data. And so, for example, if we want to select the flights that occurred on January 1st, we use filter, and then we select the data, so the flights data package. And then notice here, we have months. The sign for equal here is a double equal. We use the single equal sign for so many different other things. In here, for example, we could say, color equals origin. If you want to specify a single value of a variable, like the first month of the year, where a variable is equal to a single value, that's where you want to use the double equal sign. So in this one here, we just want all the January 1st flights, and it gives it to us. And you can see that there are 842 flights. If you multiply that by 365, you get something pretty close to our 336,000 flights. Now, here's what I mean by assigning a a variable. So if you're going to filter and you think you're going to use that data frame later, assign it to a variable name, so that every time you recall the January 1, so for example, now January 1 is a data frame. So if you wanted to work on January 1 at any time, you could just replace flights here with January 1 because it itself is a data frame. It's just a data frame that doesn't contain all the data of flights. All right, if we run this code, it's just going to give us the dimension of January 1st. So you can see it's the same thing as the dimension up here. Now, another thing we're going to do frequently, up here, you can see that this whole line of code does not have parentheses around it. Here are the rest of those comparisons. Greater than, this one here, it's the standard one. For greater than and equal to, we don't have a single character, so we have to use the greater sign and the equal to sign. Less than or equal to, and then here's the not equal to. It's just the equal sign with an exclamation point in front of the equal sign. Here's the equal sign that we talked about. If you run code and you make a mistake like this one here, notice it'll tell you. Try using the double equal so that when we run this one with the double equal, we'll get all those flights where the month is January. Okay, so a couple of Boolean operators. If you've worked with sets, probabilities, you use the union and intersection and the complement. These are set operators or Boolean operators. The first one is and. If you want to take the intersection between two sets, then you use the word and. In our language, we're going to use the ampersand. For the word or, which is the union, where we're going to kind of just combine all elements of two groups, it's just a vertical line. So you might be looking at, all flights that took off from Newark or took off in the month of January. Something like that. Two different statements. You want all flights that meet one or the other of those two criteria, so you use the vertical line. And then the exclamation point is not, and you can use it with the equal sign, so you get not equal to, but you can also use it in other contexts as well. Just a couple of questions here, and then we'll go on to answer them with the new data frame. So what about New York flights? That's what this whole data set is about. All right, to Detroit, that's the destination, DEST, on Delta Airlines. This is the carrier, right, DL. And then we want to know for this right here, what's wrong with this code. And to answer what's wrong with the code, you got to know what you're trying to display. So let's say that we're trying to display the columns or the variables of the filtered data that are New York flights to Detroit on Delta. Well, the filter here is correct. Notice that when you're going to use an equal sign, if it's a categorical variable, then you have to put quotes around it, specify a single value. But this is a single value, so you need the double equal sign. DTW, Detroit Airport, is a single value, so you need, and it's a destination. So the carrier, the destination are two variables, and you remember you always specify the flights. When we execute this command, okay, it'll give us the flights. But then here's your select command, and I'm going to bring this one up next. So what the select does is it's another one of our data manipulation. So again, you have to specify the flights, the data set, and then these are the ones that you're going to select for displaying. So let's say of the flights database, we're going to display the carrier because we want to see DL. We're going to display this destination because we want to see DTW. And let's just throw in a couple of those other variables just so you know see how it works. Now, when you do this, notice you get two different tables. You get the table generated by line 197. There it is. Notice you don't have what we're interested in terms of our table with just carrier, destination, tail number, and airtime. But when we do this one, the second one, we get the 4 columns that we ask for. So we wanted to just print the second table, but what we got are the two. And so here's one way that you can combine the filter and then print out in this display in one set of code without first printing out the entire data frame. So here's a better version. Notice I'm assigning this new data frame here, this filtered flights data, I'm assigning it to G, and then I'm going to select from G instead of selecting from all of the flights. So, and then I'm going to print those there. So now you see I just get the one table. If you want just the November and December flights, you can give it a name, November, December, and then you can assign it to all of the flights. Notice the use of in. So when you say month is in, this is like a set. So any flight that occurs in either the 11th month, November, or the 12th month, December, will be displayed. Now, remember, we have about 800 per day, and that's 60 days. So 800 times 60, that's 48,000. Let's see how close we get. 55,000, 55,4. So it gives you all 19 fields because we didn't select some for printing. Perhaps we're interested in which flights have a departure and arrival delays that are both less than 2 hours. So here's the code that would do that. You can see all these departure delays are less than 2 hours, 120. Here's another command that basically gives you the same thing. If you remember this result from probability, saying this and that is the same thing as not this or that. This particular table is going to give you the same exact table as the previous one. Yet here's a third way without using one of the Boolean operators. So when you just list some things together, they have to give values that meet both of those criteria. So you could just set your filter flights and then just list all the characteristics, arrival delay less than 2 hours, comma, departure delay less than 2 hours, and then close it off. But this one will give you the same thing. Okay, well, let's talk briefly about the value NA, not applicable, missing data. You know, sometimes in your data sets, if there is a missing data or they don't know what it is, they'll just put NA. We're assigning NA to X. So we're basically saying that we don't know what X is. And let's say if X is Mary's age, we don't know how old Mary is. Let's say, let's run this, okay. Nothing very interesting in the screen here because it's just an assignment. If I were to also put parentheses around this and run the same thing, okay, well then we get the NA. And if instead I assign the variable and then I print it, this one also will print the NA. Okay, so let's say that we also define Y, and Y is John's age, but we don't know John's age either. So both X and Y were assigned to be two different people's ages. So what if we want to know if they're the same age? So we say Mary's age is equal to John's age. Now this is a true-false statement. So it's either going to return true, the two are equal, or false, the two are not equal. We know X is equal to NA, and we know Y is equal to NA. So when we say X is equal to Y, isn't NA equal to NA? Let's see. No, it's equal to NA. So the reason for that is that NA could be a lot of different values because they represent like variables like John's age and Mary's age. So if we don't know John's age and we don't know Mary's age, then we can't really answer the question, is John and Mary the same age? So the answer that they put there, if any variable is NA and you do a calculation, you're going to get NA because you don't know the variable. So we're going to come up with a command to handle that. And the command is NA. So if we say X is NA, and then we ask the question, is X NA? Well, we just said, yes, it was NA. So is NA and if X is NA, then that would be true. And then down here, we put the exclamation point in front of it. And so this one is saying X is not NA, which is false. So when we run the first one, we should get true. And when we run the second one, we should get false. Tibble is part of the tidyverse package. And so we can use that. A tibble is like a little table. And let me come up here to Tibble. Well, Tibble is our table creator. And so you're going to create this new Tibble called df. And it's going to consist of the X. And you can see that all of these Tibble functions here, the first thing it starts off with is a call to the data set or the frame. So the first thing you have to put in these functions for Tibble is the data frame. We've defined this data frame X here. So the X is just the numbers 1 and then NA and then 3 different elements in this set X. And then it says filter that data frame. And you're going to list all of the elements that are larger than 1. NA we don't know, so we can't say that it's larger than 1. 1 is not larger than 1, so the only number in that set X that's larger than 1 is the element 3. And so since we've asked for a Tibble, it gives it to us in a table and then filters out that data set. Same thing here, we're using some of these. Remember what this means. This vertical line means OR. So we're going to say that the data value that we're after, we're filtering down, we want to make sure that the data value is not NA. We don't want to print that one. We also want to make sure that X is greater than 3. So this particular Tibble would include NA because that X is an NA. And then X greater than 1 and 3 is greater than 1. And this means OR, one or the other. And so therefore we're going to print those two in a table. So there you see it. NA and 3 were printed in the table, in the Tibble. All right, so here's a repeat of the blurb that I keep referring you to. We're going to then go into the next command, and that is the arrange command. And this is how we sort in R, sort data. If you've ever worked in Excel, you can remember that you sort by the first field, and then you sort by the second field, and you sort by the third field, and so on, and then it sorts the data accordingly. Remember, the arrange function is like the filter function. The first thing that you have to tell this function is the data frame that you want to sort. So I would encourage you to read all the information about the arrange command. I just think of the arrange command as being a sorting command. Okay, so let's take a look at a couple of examples of using the sorting command, the arrange command. So this is your basic command here with using arrange. We're going to sort by. So you first specify the data frame, and then you sort tell the fields you want to sort. So we're first going to sort by year, and then we're going to sort by month, and then we're going to sort by day. And the arrange command automatically displays the new data frame. We still have the 19 columns and the 337,000 rows. It didn't reduce any of the data from flights. It just ordered them in a different order so that we can display it. And we can't see a whole lot here. Let me just go up to the next. So this is all the January 1st flights, but let me go to the 100th here, see how hard. Now, after the 100th page, we're only on January 2nd. This would take you a long time to scroll through all this data to actually see that the sorting is making a difference. Okay, and for this one here, we're going to arrange the flights. Okay, so we're using the arrange command, and we're selecting the flights. And how do we want to sort? Well, we want to sort on this variable called departure delay. So these are, how many minutes that a flight was delayed. And we're going to do it in descending order so that the largest departure delays come first. And so we use the sort in descending order. So if you want to sort in ascending order, you just use the arrange flight and just list the variables, and it'll automatically by default sort in ascending order. But if you do want to sort in descending order, then you have to use the DESC. So as you notice from the table, departure delay is over here, and you can see that the largest departure delay was 1301. So that's there's 60. Yeah, so this is over 20 hours. So over 20-hour delay. It happened on January 9th. Yeah, it was supposed to take off at 9 a.m. and ended up taking off at 6:41 a.m. the next day. But notice these are in decreasing order. Okay, so here's a new value of X. X contains the value 5, 9, and 6 in that order. And then we want to sort this data frame by X. So notice that these numbers are not sorted now. But if we give the sort command, you can see it lists them in order. You want to sort them in descending order. The first number, the highest number comes first. All right, how does it do the sorting of the NAs? It doesn't know what the NA is. So it can't put it at the beginning. It can't put it at the end in any meaningful way. So what it does is it just always puts it on the end. So if we sort this set in ascending order, we get 2, 5, and then it puts NA at the end. If we sort in descending order, we get 5, 2, and not applicable at the end. So NA always comes at the end. All right, let's go into our next function. The next function is the select function. Let's take a look at, with the question mark, what this one is all about. And it's going to open up our help window. Let's enlarge it, and let's drag the window to make it a little bit larger so we can read what this is all about. Select is part of dplyr. Everything is an interesting command. If you want to select a couple of fields and then just tack everything else, all the other columns at the end, you can use the everything function. And there's some other, very useful pieces of this as well. I urge you to read that at your leisure. All right, so in this case, we're just going to select the columns that we want to display. So as before, when we use one of these data manipulation functions, the first thing that we indicate is the name of the data frame. And then we print only we select only the columns that we want to display. And this is typically what the data scientist does. It doesn't make sense to, if you're going to answer a question or you want a relationship, to print the entire frame every single time. So let's just select the variables of interest and only display those. Notice that every flight has a date, so it doesn't filter out any data. It just selects the ones that you want to display and print. When you have a colon, well, all of the column variables are ordered. And so if you look at the date, it's year first, and then month and day. When you put a column in there, that just means give me all the variables from year to day. So this one is also going to include month. If we want to select all the columns except for those from year to day, inclusive. So notice there's a little negative in front of there. Not those, but everything else. All right, and notice that the year, day, and time are nowhere to be found, but every other variable is there. We started off with 19 variables. If we get rid of 3 of them, we're down to 16. Okay, so you may have read that there are a couple of helper functions that you can use inside the select. And this data set has 19, we can pretty much see them all, but there are some data sets that have hundreds of columns, and you want to be able to find them quickly. If you wanted to display from the flights data anything that started with ARR, it would give you all the variables that begin with ARR, in this case, arrival time and arrival delay. You could also use a helper and say, identify some characters for which it ends. And so in the flights data, there are a couple of variables that end with time. So notice all of these variables here end in time, and it gives you the entire number of rows. Okay, and then here's another that you can use. If the flight contains anywhere DEP. So we have these departure variables, right? Yeah, but we also got this one here. DEP was in the middle. Didn't have to be in the front. Didn't have to be at the end. If anywhere it contains that. And then notice this one here. I spelled it with capital letters. In this search command here, it doesn't care. It can be uppercase, lowercase. It's kind of one of the rare times when it really doesn't matter whether you use uppercase and lowercase in R. You can also use the matches command, and you just have to put in a bunch of characters here. So we're going to select to be displayed from the flights data anything that matches CARR. And notice it's just carrier. For example, if you're not good at spelling, but you know how some of it is spelled, you can use the matches command. Okay, so if you want to rename a flight, the original variable was tail_num, and if you want to assign it to tail num, it looks something like this. So when we come down here and try to run and find that data tail_num, it doesn't exist. but that one does. So tail num now exists and tail underscore num does not. Okay, coming down here, if you want to select for displaying the time from the flights, you want this variable, this variable, this variable in that order. So you want these three to list in order. So you want them to come first instead of month, day, and year. And then at the end, you're just going to type everything else after that. So again, if you try to run this with tail num and no longer knows tail num, and so, all right, so now when we run this command and we change tail num to its new name, then you should see, okay, time hour, air time, tail number, and then everything else, and everything else consistent. So you're going to get the 19 columns, you're just going to get them reordered. Here's another example. In this case, we're creating this new data frame called ours. Here's our two characters, the less than and the dash, to create the assignment character. Then there's going to be this set of departure times, arrival delays, air times, and distance. So just those 5 fields. And then we're going to do select, and here's a use of any of. Since we've already defined vars, that when we say any of vars, it's going to go ahead and print those 5 columns. And there they are. So again, when we're working with data, we normally don't want to use every single variable in the data set. We usually want to narrow it down a little bit. So that's what we're doing here by displaying only what we want. Okay, so we're defining a new data frame. Be sure to run this so that you can use this data frame. There's not much interesting here other than it just makes the assignment, doesn't actually ask it to print the flight. But you know, if we put parentheses around here and here, and then ran the blurb again, not only would we get the assignment, but we would also get the table. So you can see that this flight it contains the same data, but only the variables that we ask for. So instead of all 19 columns, we only get 7. You see this blurb here again, and so we're going to move to mutate. Mutate is creating new variables from old and then adding them to a data frame. Remember that the first argument is a data frame, like flights or flights SML, and the subsequent arguments just basically tell us, you know, what we want to do with that data frame. And, you know, after you run these commands, you end up with a new data frame, one that might be printing the columns in a different order, one that might be adding variables, one that might be sorting the data. But in the end, you end up with a data frame. And if you want to keep that data frame that you just filtered or displayed or whatever, then you want to do an assignment so that you can use it later. Okay, so here is the mutate command, and notice that we're using not flights, but flight SML. So we only have those 6 or 7 columns, 7 columns, I believe. Then we're creating a new variable. And in the mutate function, when you make these assignments and create these new variables in here, these also will be displayed in the flight's SML data. So the gain would be the departure delay minus the arrival delay. A lot of times, maybe some pilots or airlines, they will speed up the plane if they're delayed to try to make up some time. So the gain would be the time that they make up in flight because they took off late. Speed is the standard distance divided by time in mathematics. Distance is in miles, but airtime is in seconds. So if we want to convert the speed into the standard miles per hour, we have to multiply by the 60 here to convert from the minutes to the hours. Okay, so all this does would be to add those 2 variables to that flight's SML frame. And so if we put parentheses around the whole mutate command, not only will it mutate, add those 2 new variables to the flight's SML frame, but it'll also display them. So let's do this. Now you can't really see it, but you can see that instead of 7 columns, we now have 9. And if you do scroll off to the right, you will see that those last 2 columns were added. If you don't put parentheses around, what you can do is you can make a new assignment. If you're going to see, all of this was in the previous code, but if you just take all of this and make an assignment to flight's SML 12, then we have a new data frame, flights SML12. And then if you want to view that one, we'll just view it on the screen. Again, you've got the 9 fields, and our 2 variables are listed to the far right. So here's one where we use the mutate command, and we add 1, 2, 3 variables. And so if you know the total gain that you're going to make, speed up in time, and you also know the flight is going to be traveling for this many hours, then you can say, okay, how much time can we make up per hour? If that's a lot, then that means the plane is going, much faster. So as we come over here, we'll see that the 3rd variable has been added. So if the gain per hour is negative, that means they actually lost time. Okay, transmute is another of the data manipulation functions that we have, verbs, if you will, in the dplyr suite package. And so again, I'll put these up here. And so if you're going to use transmute, you first have to specify the data frame, and then after that you're going to specify all the variables that you want to include, because usually when you when you mutate, you're adding additional variables. When you transmute, you're actually not going to print off any variables except the ones that you have listed. And so when I do transmute here, it's going to okay, go take flights. It's going to create this new data frame, but I didn't assign it to anything. So it's going to create a new data frame. It's just not going to do anything with it other than print it. So we've got our gain, hours, and gain per hour variables. The other variable we're going to add, we're going to call it, name it the destination, and we're going to include the destination variable as a 4th area. All right, and then when we run this, you'll see that we have just those 4. So transmute is very, very handy because it just prints the ones you want to print. Okay, so there's some other operators in there, particularly modular arithmetic. If you have a % sign and then a division sign and then a % sign, this gives you the quotient when you do long division. And if you just put the 2 % signs together without the dash or the division sign in the middle, then this is going to give you the remainder. If you happen to do a division problem, 13 divided by 5, then 5 goes into 13 twice, but then you have a remainder of 3. And so the quotient is 2, and the remainder is 3. And so if you do the first number, 13, and the last number, if you put the % divided by % sign, that means what is the quotient? And the quotient is 2. And when you do just the % symbols, that's going to give you the remainder. Let's look at an example, particularly from the flights data set. And let's look at the departure time. Now notice departure time, it's 5:17. And what that means is at 5:17 a.m. So it's really not useful in its current form, because we don't have the colon between the 5 and the 7 or any other time format you want to use. So what we can do when we're manipulating the data is to create these calculated fields. We could say, okay, the hour, you take the 5:18 and then divide by 100, because this number 518, if you divide by 100, the quotient is going to be 5, and that's the hour, 5 a.m. And if you use the double % command, then you want the remainder. So when you take 100 and divide it into 518, you get 18. And then if you put these two numbers together, you get the correct time of 518. So the departure time of 518 means flight departs at 518. We can transmute from the flight. So we want to report the departure time, and then we're going to do these 2 new calculated fields. All right, so we'll do it, and you can see that we get departure time, hour, and minute listed there. Just 3 different columns, but you can see it converted 5:33 into 5 hours and 33 minutes, and so on. Okay, so just a couple other commands. In this one, X is going to be the sequence of numbers from 1 to 10, and parentheses around that, so it printed them off. Notice that it would take 2 commands like this to get the same thing, assign the sequence, and then print it. Lag would just shift everything to the right and then look at the data variable to the far left. So you take this entire sequence and shift it. Well, when you shift it, there's nothing to the left. So the variable to the left becomes NA. Let's take a look at several of them together. We've got X, we've got lag X, which shifts all of these numbers one place to the right. And when we go to the one to the right, the 9 comes here, the 8 comes here, but there's nothing to come here. So what comes here is the NA. And notice when we take this 1 minus NA, well, we don't know what that number is, so we don't know what the answer is. But all the rest of these, when we subtract, we're going to get 1s. And so something interesting has happened here. Lead is the same thing, but on the other side. So we're shifting to the left. So the one that was here, let me give you this one. The one that was there gets shifted off the screen. 2 comes to this spot, 3 comes to this spot, 10 comes to this spot, whatever was here comes to this spot. We don't know what that is, so it comes in as NA. And then when you do the subtraction, you get negative 1s. So again, here you can see if you don't have negative 1, that's where there's a difference. And just a couple of other commands. We have X and we have lag X. And then this command right here says that X is not equal to. Well, if X is not equal to, these are not equal, these are not equal, so true, these are not equal, so true. But these are not equal, but they might be equal, because if NA actually means 1, then it would be false. And if NA equals some if NA is some other number other than 1, then you're going to get true, because the 2 would not match. But we don't know what that value is, so we can't say if it's a match or not. But all of these others are not matches. So when we say X is not equal to the lag of X, all of those are true. Okay, so we first define X, 3 1s, 3 4 2s, 5 3s, and then a 4. We just basically bring down our list, and then we print it. So these first 2 commands we print, and then we do the lag. We can see this, it shifts everything to the left. And then when we look at X is equal to lag X, we got a bunch of trues. Okay, so if the 2 are equal, then we're going to say true. If the 2 are not equal, we're going to say false. So we don't know what this is, so we have to say not equal to. These 2 are true, these 2 are true, these 2 are false. So true, true, false. So if we're programming, if we ever see a false, that's where we know that there's a number change. I want to show you how to use the sum feature, because you're going to use it a lot. So you can see our data set here. It consists of these 11 elements. The numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But in the 6th spot here, we have an unknown variable NA. And so when we run this piece, you can see that it first prints off my list here, and then it adds up all those numbers. Now we know that all these numbers add up to 55 here, but it's like saying if you sum up all these numbers and you don't know one of the values that you're adding together, then the result you're not going to know. The sum you're not going to know. So that's why it gives you an NA here. All right, so let me introduce you to the is NA function. So if you say for each one of those X, is it an NA? Well, it says no, 1 is not an NA, 2 is not an NA, blah, blah, blah. But when you get to the 6th element here, after 5, you have 1, 2, 3, 4, 5 falses, and then the true. So it's saying that that's the NA, and then it goes back to false after that. Now, when you take the sum of all the NAs, this works in an interesting way. Remember that is NAX is all of these trues and falses. And when we take the sum of all these trues and falses, we get 1. Well, what's happening here is that function sum x, the sum is NAX, basically just counts up the number of trues. So we can know basically the number of NA values in the list. NA.rm means to remove the NAs. So if we want to remove the NAs, we just say NA.rm is true. Then it removes all the NAs. So because this is attached to the sum command, it's now going to add up all the numbers except the NAs. And if it doesn't add up the NAs, it can do the calculation. And so here you can see that the calculation is 55, which is what it should be. The complement of is NA is not NA. And so notice the true false sequence here is just the opposite of the true false sequence here. Then when we add, just like when we summed up the is NAs, when we sum up the is not NAs, this is going to count the number of non-NA data values, so the number of falses. Here's the cumulative sums right here. So as you start with the first one, the sum of the first number is 1. The sum of the first 2 numbers is 3. The sum of the first 3 numbers is 6. We're accumulating the sum, cumulative sum. Now, when you add the first 5 numbers here, you get 15. But when you add the first 6, and every time after that, you're going to be adding an NA. So it doesn't understand an NA. Okay. All right, let's do cumulative sum again, but let's redefine a different X. Here's our X, and then we're going to add up the cumulative sum going along. These numbers down here are known as the triangular numbers. All right, now the cumulative mean means that we're going to calculate the mean of the first set of numbers. So if we just have one number, one data value, and we say, what's the mean? It'll come back and say the mean is 1. If we take the first 2 numbers, 1 and 2, and take the average of those 2, well, that's just the midpoint of those 2, and we get the average of 1.5. Again, we're accumulating, so in the next one, we take the sum of those numbers, divide by 3, and we get 2. So you can see the pattern here. Cumulative product, we're going to accumulate a product as we go through, and notice that's exactly what the factorial does. So 1 times 1, or just 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, and so on. That generates the factorials. Cumulative minimum. So as we go from one data value to the next, we consider all those data values. So what's the minimum if we just look at that data value? What's the minimum if we look at the first 6 items? All right, and then if we do the cumulative max, then we say, well, if we're just looking at the numbers 1, 2, 3, what's the maximum between those 3? Well, it's 3. If we look at 1 through 7, what's the maximum of those 7 numbers? Well, it's 7. So it turns out that cumulative max is the same thing as X. Okay, here we define a new Y. It does have some 1s, 2s, 3s, 4s, 0s. They're in various orders, and we're going to introduce the ranking command. So sum of is not NAY basically counts up the number of non-NAs in the data frame. All right, then for each Y, we can do this minimum rank. This creates another data frame. All right, so here's how it works. Now 0 is the smallest data value, so it's in rank 1. And then 1 is the next one, so it's ranked 2. And then for these 3, they're all the same, so they're all ranked 3. And then this, but there are 3 of them, so even though they're all equally ranked, they cover 3 positions. So this is like rank 3, rank 4, rank 5. So the next rank for 3 would be 6, and the next rank for 4 would be 7, and we're not going to give NA a rank. Min rank, and kind of the same thing, but now we're going to consider the data values in descending order. And so the largest data value is 4. So it gets rank 1. And then 3, it gets rank 2. And then we've got these 3 2s. They're 3, but remember they take 3, 4, and 5. And so the 1 would be in position 6, and so on. Another command is row number. Okay, so let's see what this one does. Notice we print off the Y frame along with the row number frame. And so if you did a tibble and you listed all those numbers in order, 0 would come first, followed by 1, and then 2, and then you got the 3 2s. But the difference between the min rank Y and the row number Y is row number also ranks it, but for the 3 2s, it has to put them in rows, and so it gives them rank 3, 4, and 5, and then 6 and 7. Dense rank is just a variation of that. So if we do dense rank, you can see what happens is it condenses all of the same value variables just to one position. And so all of these 2s just get delegated to position 3, and we don't give them their own row 3, 4, and 5. And one other cumulative distribution. So you can get a sense of what's happening here. You've got a listing of the Y values, and if you count those values, you'll see the NAs in anywhere. And when you count the number of values in Y, you'll see that there are 8 of them, but 7 of them are NAs. And so 0 is ranked first,
out of 7, and 4 is ranked 7th out of 7, and 3 is ranked 6 out of 7, and then you got the NA, and then these 3 here are all ranked 5 out of 7,